amplification of noise. Mathematically, that's identical to minimizing this. This is weighted damped least squares. Mathematically, that's equivalent to doing normal least squares, only you stop iterating before the noise grows very large. Mathematically, that's equivalent to minimizing this, which is least squares plus a little augmentation that has to do with the model length. So you can just run your Levenberg-Marquardt algorithm, but only minimize this instead of minimizing least squares. Mathematically, that's the same as solving this system of equations for m. And we can do that. We know how to solve systems of equations for m. So I want to talk about some applications. This is a picture of the Hikamarka Radio Observatory. It's a short drive from here. It's operated by the Peruvian Geophysical Institute. And it's the world's largest radar. And it's a megawatt-class radar. The dimensions are 300 meters on the side. It's been here since the early 1960s, and it's used for probing the upper atmosphere. But the problems that we face in interpreting the data tend to be inverse problems. Here's one problem. We have a theory for what the spectrum of the scatter looks like when we scatter off of ionization in the upper atmosphere. I've just plotted some spectra here. Depending on the temperature, the density, the composition, drifts, other things, we can predict very well what the spectrum should look like. Equivalently, the autocorrelation function we can predict. But when you perform a radar experiment, so here's a diagram of a radar experiment. Here's the radio wave going up into space. Here's the scatter coming back down into space, from space. Here you are making samples, making measurements. You can measure an autocorrelation function here, but when you measure things in time, you're measuring not only time, but you're measuring altitude. The time that you make a measurement depends on time, but it also depends on altitude. And altitude and time are conflated together in a complicated way. These functions show how different lags of the autocorrelation function are convolved with these funny shapes. This dimension is altitude, this dimension is lag. So when you try to measure an autocorrelation function with a radar, you measure something that has undergone a two-dimensional convolution with one of these shapes. So here are data that we measure at Hikamarka. This is altitude. This is 3,500 kilometers. And these different lines are different lags of autocorrelation functions that have been convolved with those terrible instrument functions. This, by the way, is a satellite. What we'd like to do is perform a deconvolution, and when we do that, and we use our model of what the autocorrelation function should look like, we get terrible results unless we apply these inverse methods. And in the inverse methods that we use is we minimize the model prediction error, that's just nonlinear least squares, but we also minimize the roughness of the electron and ion temperatures. We also make sure the ion temperature is never less than the electron temperature, which physically would be impossible. We also minimize the roughness of hydrogen ions. The ionosphere is made up of mainly of oxygen, hydrogen, a little helium. And then the last thing we do is we make sure that all of the species have fractions between 0 and 100%. Mathematically, there's nothing that prevents them from being outside those, but of course physically they have to be inside those. So here are the results that we get. This is altitude. This is 1,600 kilometers, 200 to 1,600. This is electron density in the ionosphere. It's hard to tell, but the black is electron temperature. The red is ion temperature. This black is hydrogen ion fraction. And the blue is helium ion fraction. There's not much helium. So it works. And Hikamarka is virtually alone in the world. Hikamarka and the Arecibo telescope in Puerto Rico are really the only two facilities in the world that can measure these parameters to these altitudes with this precision. But it requires inverse methodology. There's one other strategy for inverse methods, which is statistical. It's called maximum a posteriori method. It uses Bayes' theorem, and it's probabilistic. And it says when we try to find the model that matches our data, we'll maximize the probability of the model conditioned on the data. By Bayes' theorem, that's the probability of the data conditioned on the model times the probability of the model. It's easy to calculate the probability of the data conditioned on the model. That's just the chi-squared parameter if all the errors here are normally distributed. What about the probability of a model? What's the probability of the thing that you're trying to measure? Well, there are a lot of possibilities. One of them is rooted in entropy. And entropy is a measure of how many different ways the thing that you're trying to model can be assembled at random. And so this is an expression for the entropy. Again, it's just a measure of how many different ways the solution that you find could have been assembled at random. And our preference is for solutions that have a high entropy, that could come about naturally by chance very easily. And so one just maximizes this whole thing here. You write down a cost function that involves the entropy. It involves the model prediction error, the difference between the data you have and the data that you think you have. And then also a metric over here that forces the errors to be no bigger than they really should be based on your estimates. And you take this equation and you just find its extremum. And when you're done, you have found the model that has satisfied the map condition. So we're going to use that to study this. These are more Hikamarka data. These are data from about 500 kilometers altitude, and it shows a phenomena that occurs very often at night. And instead of nice uniform density, temperature, and composition profiles, what happens is the atmosphere becomes very turbulent, much as you have in a convective thunderstorm on the ground, or a tornado, or a hurricane. And lots of plasma turbulence arises, and we start getting very, very, very strong radar scatter from the turbulence. This is not described by the theory that I showed you before. We don't have a theory to describe this turbulence, but it's there. Here I'm showing this turbulence as a function of altitude and time. But of course, the turbulence is heterogeneous in space. It looks interesting in space, too. And we'd really like to make a picture of what this looks like in space. What I'm showing is not a picture here. This is a record of altitude and time. What we really like to do is to make an image. We can do that at Hikamarka because Hikamarka is very modular. And you can divide the antenna, shown here, into lots and lots of small antennas. And it turns out from the data received on all these small antennas that are separated in space, you can synthesize an image of what's going on above. You can synthesize a camera. You can sort of synthesize an aperture plane here. But the process involves data inversion. So we measure scattered signals on 2 antennas separated in space, average the product up for a while. That is related to this quantity, which is an integral transformation of this. This is called the brightness, and this is a description of where in space the echoes are coming from. So we have lots of antennas. We can build up this function. It's related to this thing that we want through this integral transform. This integral transform is complicated, but it's almost a Fourier transform. So in the end, we just have the problem of inverting a complicated Fourier transform, only using data that are a little noisy and that are sparse and that are sort of incomplete. But we apply the map method that I showed you before, and we can actually generate images of what's going on overhead, and here they are. So it's hard to read. This is altitude. This is 750 kilometers. And this is angle. This is bearing. These are looking at different places. And here's a picture of what the plasma turbulence looked like in the area right over the radar, illuminated by the radar. Here it is at one time, here it is at another time, here it is at another time. The colors tell us about the Doppler shift, which tells us about the drifts, the motion. And the brighter the pixels, the more backscatter we're getting. These are just created in snapshots of time. It takes about 3 seconds or so to create one of these images. So it's like a photograph and then another one and another one. But we can assemble the photos and make a little animation. And if we're lucky, there you go. So these are animations of the plasma turbulence over Hikamarka as a function of time. There are thousands of frames here. It took quite a few hours to do the computations. But the computations just involve the inverse method that I've shown you. Here's another one. So there's a tremendous amount of detail in here. Each pixel is about 500 meters by 500 meters. And the time steps are about 3 seconds. So our hope is that by studying this kind of imagery and building some numerical models of what's going on, we will learn to understand and ultimately forecast